Let's consider a dilute gas for which the temperature is increasing from bottom to top on the z-axis, as you can see in this figure. So when you consider z is equal to constant plane, you will find that the molecules coming from above this plane will have a higher mean energy than the molecules coming from below this plane. So the heat transfer will occur due to this difference in the mean energies. So we're assuming that we have a dilute gas for which the temperature gradient is positive. So this implies that a molecule that is coming from above, as z is equal to a constant plane, has a mean energy, that's the mean energy per molecule, which depends on temperature, that is larger than a molecule that is approaching this plane from below. So this molecule is coming from below. So because of this energy difference, we will have a net transport of energy across this interface. Now, how many molecules will transport energy from above the z is equal to constant plane, and how many from below? Once again, neglecting the velocity distribution, we can basically see that on average 1/6 of the molecules, so n times v bar, so this 1/6 factor once again comes from the independent degrees of freedom x, y, z, and now we're moving in a certain direction on the z-axis, so z minus z or plus z, so 1/3 times 1/2, we get 1/6. And n is the number of molecules per volume, and v bar is the mean speed of a molecule. So we have therefore the flux of molecules that is equal to 1/6 nv bar. So a molecule, when it is above the z is equal to constant plane, has changed its mean energy at a mean difference of a mean free path L above the z is equal to constant plane. So this L is my mean free path, and basically I see that at a distance z plus L from the bottom, so this is my z is equal to 0 reference. So I have z is equal to constant plane. I have the last collision that occurred at z plus L, and then these molecules are transporting this energy to z is equal to constant plane. And similarly, for molecules coming from below, the last collision occurred at a mean distance L from the z is equal to constant plane at z minus L. So they're transporting the energy epsilon bar at z minus L. So there is the corresponding temperature T at z plus L. So I'm assuming it is hot here, and it is cold below at z minus L. Okay, so we can basically say that the mean energy that is transported per unit area per unit time across the plane, so across this z is equal to constant plane, from below. So what is the mean energy transported from below per area per unit time? So it is the particle flux 1 over 6 mv bar multiplied by the mean energy per molecule epsilon bar, which has its last modification at z minus L. So epsilon bar z minus L. And similarly, we can talk about the mean energy once again that is transported per unit area per unit time, that is due to the motion of molecules that are approaching the plane from above. So across the plane from above, this will be equal to 1 over 6 nv bar epsilon bar. The last collision occurred at z plus L, so epsilon bar value at z plus L. So therefore you can see that the heat flux, the amount of energy that we're transporting per area per unit time, will be 1 over 6 nv bar, the particle flux, times the energy that is entering the plane from below, epsilon bar z minus L minus epsilon bar z plus L. So this is the heat that we're transporting in the positive z axis. But in fact the heat transfer will occur from top to bottom, as you know. So we can use the same trick we used for our previous discussions on viscosity and as well as the diffusion process, diffusivity. So epsilon bar at z plus or minus L, the mean free path, can be expanded around L is equal to 0, or we can say that L much less than z limit. So this is basically epsilon bar at z, and then we have the derivative plus or minus del epsilon bar del z times L. Again, this is Taylor expansion. It's a first degree approximation. So we can look at the heat flux Qz. This is again the particle flux 1 over 6 mv bar, and for the energy that is coming from below, epsilon bar z minus L, I substitute approximately epsilon bar z minus del epsilon bar del z times L, and for the energy that is approaching from above, minus epsilon bar at z minus del epsilon bar del z times L. So minus, but in parentheses we have a plus, so the minus is distributed. So we obtain this result. So we see that these mean energies at z cancel, so that the heat flux is minus 1 over 3 nv bar L del epsilon bar del z. And now we can basically look at the derivative with respect to temperature. So epsilon bar is a function of temperature. So we can write this heat flux as minus 1 over 3 n v bar L del epsilon bar del T del Z. So del epsilon bar del T, the derivative of the mean energy of a molecule with respect to temperature, is C, which is the heat capacity at constant volume, that is per molecule. So this is basically an intensive quantity. Therefore, we find that the heat flux we have is minus 1 over 3 n V bar CL del T del Z. So this quantity in parentheses is our thermal conductivity kappa, which is 1 over 3 n V bar CL. Okay, so n is the number of molecules per volume, n over v. V bar is the mean speed per molecule. C is C, we have defined heat capacity at constant volume per molecule, and L is our mean free path. Okay, so we can see that we can obtain a very simple result for the thermal conductivity in terms of the number density, the mean speed, the heat capacity per molecule, and the mean free path. So it's very similar to the discussion we had on viscosity. So let's review what we said. We have a dilute gas where the temperature is increasing from top to bottom. So we are defining our reference direction for the heat flow. So heat flux is defined in the positive z direction, and at the end I have obtained a minus sign. Del T del Z is positive because the heat flux will occur from the hot side to the cold side as usual. So you have a mean molecule, one molecule which has a mean speed v bar, which is approaching a z is equal to constant plane from above, and one molecule from below. When these two molecules meet at this z is equal to constant planes, there will be energy transfer because one has picked up an energy at z plus L due to the last collision it had at z plus L, and the other one at z minus L. So the mean energy will be less for the one that is coming from below because the temperature is smaller than the one coming from above. So the mean energy transported per area per time across the plane, so that's the energy flux, 1 over 6 nV bar epsilon bar z minus L from below and epsilon bar z plus L from above. So the net heat transported is 1 over 6 nV bar per area per unit time. It will be epsilon bar z minus L minus epsilon bar z plus L. And this epsilon bar z plus or minus L can be expanded using Taylor's series if we assume that this z is equal to constant plane is sufficiently above the bottom where we have the mean free path is much less than z, which is usually the case. So we can find that the heat flux is minus 1/3 nV bar L del epsilon bar del Z, but epsilon bar is a function of temperature, so basically by recognizing that del epsilon bar del Z is del epsilon bar del T del T del Z, del epsilon bar del T is the heat capacity per molecule at constant volume. So we have for the thermal conductivity 1/3 nV bar CL. It's a positive quantity, and the heat flux is, as a result of having del T del Z positive, a positive temperature gradient is going to be negative as expected.